Tree rotation is a fundamental operation in computer science, particularly in the context of binary search trees, BSTs, and self-balancing trees such as AVL trees and red-black trees. Tree rotations are used to maintain or restore balance in a tree, ensuring that operations like insertion, deletion, and search remain efficient. The height of a BST directly influences the time complexity of these operations, and an unbalanced tree can degrade performance from O log n to O n. In the worst case, rotations adjust the structure of a tree without violating the binary search tree property, meaning that for any node, all keys in the left subtree remain smaller, and all keys in the right subtree remain larger. There are primarily four types of rotations: single right rotation, single left rotation, double right left rotation, and double left right rotation, though the names may vary slightly in different texts. Understanding each type and its effect on the tree structure is crucial for implementing efficient, self-balancing trees. A single right rotation, sometimes called a clockwise rotation, is used when a subtree becomes left-heavy due to insertion or deletion. In this case, the left child of the unbalanced node becomes the new root of the subtree, and the original root becomes the right child of the new root. Any right subtree of the new root is moved to become the left subtree of the original root. For example, consider a node X with a left child Y that has a left-heavy subtree. A right rotation around X makes Y the new root of the subtree, with X becoming Y's right child. This rotation decreases the height of the left-heavy subtree and restores balance locally while preserving the BST property. Single right rotations are particularly effective for left-left LL imbalance cases, which occur when nodes are added to the left subtree of the left child. Conversely, a single left rotation, also called a counterclockwise rotation, is used to correct a right-heavy subtree, typically after an insertion into the right child's right subtree. In a left rotation, the right child of the unbalanced node becomes the new root of the subtree, and the original root becomes the left child of the new root. The left subtree of the new root is reassigned as the right subtree of the old root. For instance, if node X has a right-heavy child Y, performing a left rotation on X makes Y the new root and X its left child. This reduces the height of the right-heavy subtree and resolves right-right RR imbalance, helping to maintain O log n operation times in self-balancing BSTs. Double rotations are used when a subtree experiences more complex imbalances that cannot be fixed by a single rotation. A left-right LR rotation occurs when a node is left-heavy but the imbalance exists in the right subtree of the left child. In this scenario, a two-step rotation is performed. First, a single left rotation is applied to the left child, converting the imbalance into a left-left case. Then, a single right rotation is applied to the original root to restore balance. For example, if node X has a left child Y with a right-heavy subtree Z, performing a left rotation on Y, followed by a right rotation on X, rebalances the tree while preserving the in-order traversal sequence. The left-right rotation resolves left-right imbalances that cannot be fixed by a single rotation alone. Similarly, a right-left RL rotation addresses right-left imbalances, which occur when a node is right-heavy but the imbalance lies in the left subtree of the right child. The RL rotation is performed in two steps. First, a single right rotation is applied to the right child, converting the imbalance into a right-right case, followed by a single left rotation on the original root. For example, consider node X with a right child Y that has a left-heavy subtree Z. Applying a right rotation on Y, followed by a left rotation on X, restores balance while maintaining the binary search tree property. Right-left rotations are essential in maintaining efficiency in AVL trees after insertions or deletions in specific subtrees. Tree rotations are not only used in AVL trees but also play a critical role in red-black trees, which use rotations combined with recoloring to maintain balance properties. Red-black trees allow slightly more relaxed balancing rules than AVL trees, but rotations are still necessary to prevent long paths from developing. For instance, after inserting a red node, a rotation may be needed to fix consecutive red nodes that violate red-black tree properties. Both single and double rotations are used depending on whether the violation occurs on the left or right subtrees. Rotations in red-black trees are always combined with recoloring, making the process slightly more complex than in AVL trees. But the underlying principles remain the same. Rotations restructure the tree without breaking the BST ordering. Rotations have a significant impact on the height of the tree. By performing rotations strategically during insertions and deletions, self-balancing trees ensure that the height remains O log n, which is crucial for maintaining logarithmic time complexity for searches, insertions, and deletions. Without rotations, insertions in a sequentially ordered set of keys could create a skewed tree, effectively reducing a BST to a linked list and increasing operation times to O n. Properly applied rotations redistribute nodes across subtrees, ensuring that no path becomes excessively long relative to others, thus optimizing tree performance. In addition to balancing, tree rotations are also used in splay trees, a type of self-adjusting BST in splay trees. Rotations are performed to bring recently accessed nodes closer to the root, improving the average access time for frequently accessed elements. Splay trees use combinations of single and double rotations, referred to as zig, zig-zig, and zigzag rotations, to restructure the tree based on access patterns. These rotations are different in purpose from AVL or red-black rotations but operate on the same principle, reassigning nodes while preserving the BST property. In conclusion, tree rotations, whether single right, single left, left right, or right left, are fundamental operations that maintain balance in self-balancing binary search trees. They preserve the in-order sequence of nodes, ensure logarithmic height, and optimize the efficiency of insertions, deletions, and searches. Rotations are widely applied in AVL trees, red-black trees, and splay trees, demonstrating their versatility in maintaining dynamic, ordered data. Understanding all types of tree rotations and their application is essential for implementing efficient and robust data structures that handle dynamic operations while keeping performance predictable and scalable. These rotations are at the heart of tree balancing algorithms and are indispensable for any computer scientist or software engineer working with advanced data structures.